We've been looking at statistical significance, and to this point we have assumed that the dependent variable that we're analyzing is interval level dependent variable. We can use the 95% CI, we can calculate p-values and get very precise estimates of how often we would observe the pattern that we're seeing under the assumption that the null hypothesis is correct. That knowledge is going to serve you well when we get to regression analysis as well. But what if we don't have an interval level dependent variable? What if we're doing cross-tabulation analysis and we have nominal or ordinal level variables in the table? That's where the chi-square test comes in. The chi-square test is perhaps the most commonly used statistical test in cross-tabulation analysis. It's one of the oldest tests of significance still in existence or still in use. The chi-square test determines whether the observed dispersal of cases depart significantly from what we would expect to find if the null hypothesis were correct. So in this way, the logic of hypothesis testing is the same as before. The null hypothesis is here. The null hypothesis has an expectation about what the data can be expected to look like. And then we compare our observed cases, our observed dispersal of cases with what the null hypothesis expects us to find. Let's look at a crosstab here. This tests the hypothesis that men and women will have different views of diplomacy versus military force. We have 530 females here, 511 males, and if you're just without any knowledge of chi-square, if you're looking at this table, you would say, well, let's see, about 46.2% of females favor diplomacy versus force, compared with 34.4% of males. So, there's over a 10-point drop, about a 12, almost a 12 percentage point drop in the preference for diplomacy across genders. So we would be tempted or inclined to say that our hypothesis, our gender gap hypothesis, is supported. But the null hypothesis would say, not so fast. The null hypothesis says, look, the overall distribution of cases, over here in the total column, this is called the marginal distribution of the dependent variable. Overall, 40.4% of the entire sample said diplomacy, 25.6% of the sample took the middle position, and 33.9% of the sample said force over diplomacy. So the null hypothesis focuses on this marginal distribution of the dependent variable and says this. It says, well, if 40.4% of the total sample favored diplomacy, that means that any way you divide up this sample, by gender, by race, by income, by education, 40.4% of whatever category you're looking at will favor diplomacy over force. So, for example, the null hypothesis says you can expect to find 40.4% of these 530 females to favor diplomacy. You would expect 25.6% of these females to be in the middle position, and you would expect 33.9% of these females to be in the force category. Any departures from those expectations, as we've seen here, are explained. Any departures are explained by random sampling error when the sample was taken. So the null hypothesis, the first thing about chi-square is you replicate these percentages down each of these columns and then compare what we observe with what the null hypothesis expects us to have found. That's the logic. H sub 0 is based on the expectation. So again, we're expecting the null hypothesis to be true. We're according it that respect. H0 is based on the expectation that the distribution of cases down the female column and the distribution down the male column will be the same as the distribution down the total column. So 40.4% of females and 40.4% of males will say diplomacy, 25.6% will take the middle position of both genders, and 33.9% of both genders will say force. Any observed departures from this expected pattern are accounted for by random sampling error. So that's the setup. We have to determine first what the null's model of the world, what would the data look like if the null hypothesis were correct, and just how far does our observed data depart from that expectation. Now, here's the calculation, and I know it looks a little intimidating, and indeed it is tedious, but let's work through it because you'll get a real intuitive feel here for the chi-square test statistic. There's chi-square, capital Chi, Greek letter, squared. It says to do this. For each cell in the table, take the observed frequency of cases, that's F sub O, the observed frequency of cases, subtract the expected frequency of cases, and we'll look at how to derive the F sub E here. These are the expectations under the assumption the null hypothesis is correct. Subtract FE from FO, square that amount, square that value, and then divide it by the expected frequency for each cell. Each cell then has a value, a number in it, that summarizes departures or concordance with the null hypothesis expectations. I've just got the steps here. So for example, take an example here. Find the expected frequency for each cell. For example, since 0.339 of the total sample fall into the force category, the dependent variable, the expected frequency for the female force cell would be 0.339 times 530, or about 180. We'll come back to that slide. Here are all the calculations for the entire crosstab. Here's the female force cell here. Here's the 160 females that actually were observed to have fallen in this cell. Here's the expected frequency. Where did this come from? We multiplied 0.339, since that's the proportion or the percentage for the entire sample, times the number of females, and we came out with about 180, 179.7. But I just want you to get an intuitive feel here for where these come from. So for example, getting back to our example, we observed 160 females. We expected based on the null hypothesis about 180. If you subtract 180 or 179.7 from 160, that's the next part of the formula, you get about minus 20, minus 19.7. If you square that, you get 388. And then if you divide the 388 by the expected frequency, which is 179.7, you get a value of 2.2. So for this cell, the null hypothesis was off by 2.2. Is the sort of the resolution for that cell. The null hypothesis said, well, you should have gotten 0 here. You got 2.2, but you got 2.2 because your departures from expectations occurred by chance. Notice the calculation for every cell. If you go back to the formula, the overall statistic for the table is determined by summing up all those cell-by-cell calculations. All right. Now, so we add all those cell-by-cell calculations up. We add them up, and we get a value, an aggregated summed value of 15.2 for all those numbers. So what? The null hypothesis says it should have been 0, give or take random sampling error. How do we figure out the amount of random sampling error that's contained in that 15.2? That's a complication in chi-square that you don't run into when you're doing normal estimation. Let's talk about it. The size of the chi-square statistic that is needed to, and I'll just say beat the null hypothesis, depends on the degrees of freedom in a table, or the number of rows and columns of a table. The more numbers, the more rows and columns that a table has, the greater the degrees of freedom, and the calculated value of chi-square that you need to beat the null hypothesis is higher. Degrees of freedom for any table is equal to the number of rows minus 1 times the number of columns minus 1. So in our example, we have 3 rows, 3 minus 1 is 2. We have 2 columns, 2 minus 1 is 1, yields 2 degrees of freedom. The number of degrees of freedom determines the shape of the distribution. Unlike the normal distribution, which always assumes the same shape, the chi-square distribution depends on the structure of the table, the number of degrees of freedom. I found this interactive chi-square applet that has been provided by Professor Matt Bogner at University of Iowa. We thank you, Professor Bogner, for this. Open this up. Now, for example, our table has 2 degrees of freedom. Let's just put 2 in there. Here's what the distribution looks like for 2 degrees of freedom. It's an odd-looking distribution. As you go out here, you wonder at what point, these are calculated values of chi-square along the base here. How big does the calculated value have to be to get out to where there's only 5% of the curve remaining? So what's called a critical value, the value that you have to beat in order to reject the null hypothesis, depends on how many degrees of freedom you have. Okay. Let's put 5 in here just to show you how this distribution changes. Now the chi-square distribution looks different, and you can see the shape. Now the 0.05 region is going to be out here somewhere. Looks like about beyond 11 would be about 5% of the curve. And again, let's put 10 in here. I mean, now chi-square is starting to look almost symmetrical, and at certain levels of degrees of freedom it does approach a normal distribution. The current point, though, is as we go out into the frontier, notice these calculated values of chi-square now are much higher. That for tables that have a lot of rows and columns, it becomes more likely that random probabilities are going to produce departures from expectations, and so we have to accord the null hypothesis more and more territory. It looks like we have to go out here almost to 18 or 20 to get into the region of the curve that is in the 0.05 level of significance. In fact, let's go back to 2 degrees of freedom, and let me illustrate something here. I'm going to put a number in here. That says chi, or it says x, but it stands for a calculated value of chi-square. I'm going to type 5.991, and I'm going to hit enter. And it says the probability above that value of a 5.991 is 0.05. Here's the value I put in of 5.991, and this is in the pink area here. This is the 0.05 region of the curve. Let me put 5 in here again, and I'm going to put in the value 11.07, and again it says 0.05. So whereas before we had to get a calculated value of chi-square that was greater than 5.99, now when the table is larger, has 5 degrees of freedom, we have to be all the way out here at about 11.07 to return 0.05 to the right. One more example. I'll put in 10. And the critical value here is 18.307. Hit enter. And again, we get 0.05 all the way out here. So for a table that's very large, with a lot of rows and columns, and for which random probability, random chance is going to create a lot of noise in the table, you have to have a calculated value of chi-square that is greater than 18.307 in order to defeat the null hypothesis. These numbers that I've been practicing with here, the first one was 5.991, the second example was 11.07, that was for 5 degrees of freedom, and the current one, which is 18.307 for 10 degrees of freedom, these are what are called critical values. A critical value is a value that defines the boundary between the null hypothesis' territory and the rejection of the null hypothesis. In this example, and let's go back to the one that we're using here, this is what the curve looks like here. For this example, if we have a calculated value of chi-square that exceeds 5.991, that's the critical value, we would reject the null hypothesis. In this case, we're going to reject it because our calculated value for our table was 15.2. So the critical value approach is much like the 95% CI approach. It gives you a number, of a level of confidence, a number that defines the confidence that you have in rejecting or not rejecting the null hypothesis. In our example, the null hypothesis owns all the territory between a calculated value of 0 all the way out to 5.991. We own, the alternative hypothesis owns all the territory beyond that out here in this region of the curve. Also, I can demonstrate here. Let's put in the actual value that we calculate. We can get a p-value. The computer analysis that you are probably going to be doing will return a p-value, probability value, or a sig value. I'll put in 15.2, and here this applet returned 0.0005. Under the assumption that the null hypothesis is correct, we would obtain that the observed data that we got in that table about gender and diplomacy versus force looks like 5 times out of 10,000 by chance reject the null hypothesis. Just to review, a critical value marks the upper plausible boundary of random error and so defines H0's limit. So just look at it that way. The null hypothesis gets all the territory between 0, which the null hypothesis said we should have gotten as a calculated value of chi-square, and all the territory between 0 and the critical value, and the critical value depends on the number of degrees of freedom. Example, using the 0.05 level and 2 degrees of freedom, the critical value, as we just saw, is 5.991. The calculated value of chi-square, 15.2, exceeds the critical value, so we reject the null hypothesis. This is a detail of table 7-8 in the text, and it shows you critical values of chi-square at different significance levels. We've been using the 0.05 level of significance here, and you can see as the number of degrees of freedom goes up, the critical value of chi-square goes up. Circled is the one for our example.